Good afternoon, and thank you for attending the November Transportation U event. Transportation U is a national hands-on interactive mentoring program that offers girls ages 13 through 18 an introduction to a wide variety of transportation careers. It is connected to Women's Transportation Seminar, or WTS, which is a women's organization for transportation professionals. I am Michael Book, a strategic communications specialist in HDR's Phoenix office. HDR is an international company which specializes in engineering and architecture services. If you have any program or event questions, you can send me an email at michael.book@hdrinc.com. My email address is being placed in the chat right now. This event is also supported by Basha, event specialist at WTS International, and Bree Balke, community relations coordinator at Valley Metro. So at this time, I would like to ask if you are a teacher hosting a group of students to please send me an email with your school, city, and the list of participating students. At the end of the program, we will be randomly drawing one student's name to win a prize. And if you are a student who is logging in on your own, you can also type your school, city, and name in the chat to be able to win a prize. So each June, Transportation U has a summit, typically in Washington, DC, although last year was online. And I will be selecting one student to go on the trip with a mentor who will also be selected in the next few months as well. The eligibility for attending the summit is being a female student and who is currently a junior or senior in high school. So the Metropolitan Phoenix WTS chapter does pay for the expenses for the student to attend the event, which features a variety of transportation speakers and facility tours during the summit. It is a really great experience if you're interested in pursuing a future in the transportation industry. And the way to have a chance for this is to continue attending these events. And secondly, to write a 500-word essay about what interests you about the transportation field and how the summit would benefit your future career. So please feel free to begin working on your essay over the holiday break. The deadline for submission will be February 28th, 2022. And another note, we will not be having an event in December due to the holidays. And as of right now, there is no event scheduled in January. However, I am currently working on that. So there should be something scheduled relatively soon, and I will make everyone who attended this event aware of that. Now for today's event, Paul Basha has 47 years of traffic engineering and transportation planning experience, with approximately half as a consultant and half as a public servant. He also has been a faculty associate at Arizona State University for 25 years. Paul served on the evaluation committee for the Parking Generation Manual 5th edition, the Trip Generation Handbook 3rd edition, the Trip Generation Manual 10th and 11th editions, and the ITE Warehouse Trip Generation Expert Panel. Paul has written 6 articles published in the ITE Journal, the most recent in the October 2021 issue. He has also spoken at 31 professional meetings, including a poster presentation at the 2021 ITE International Annual Meeting and full presentations at the 2010 and 2014 ITE International Annual Meetings. So Paul, thank you for joining and presenting to our Transportation U AZ group. How are you doing today?
Doing great, Michael. It's very good to see you and see all the students. Thanks very much for the invitation and a great introduction.
Thank you.
Shall I begin?
Yes, go ahead and get started.
Oh, something didn't go quite as
there you go.
planned.
Perfect.
All right, everybody can see the beginning of my presentation.
Yep, looks good.
Great, thank you. As Mike said, I'm a practicing traffic engineer, and what I want to discuss with you today is how I use high school mathematics in my work as a traffic engineer. The purpose is to ensure safety on our streets. Every traffic engineer wants to minimize collisions. Collisions are not healthy for anybody. So I use mathematics to prevent collisions. I will show you 3 different circumstances where traffic engineers use mathematics to ensure safe, efficient streets. If you need to ask me questions, I will have some time at the end of the presentation. Also, my last slide will have my name and email and phone number. And finally, you can certainly send Mike an email and he can forward that on to me. So here we go. Everybody wants a green light. Nobody wants a red light. That's quite a dilemma. But as traffic engineers, we can use high school geometry to give as many people as possible green traffic lights. What we use is called a time distance diagram. So I'll be showing you a brief introduction to time distance diagrams. I want you to know that this presentation I just gave a few weeks ago in the graduate level course I teach at Arizona State University on this very topic. Hopefully you all remember Cartesian coordinates, and be sure to thank your high school and middle school mathematics teachers for teaching you about Cartesian coordinates. You remember them. We've got 4 different quadrants, 1, 2, 3, and 4, and we've got an x-axis and a y-axis. I want you to think about those 4 quadrants a bit. And remember what's different about quadrant 1 compared to 2, compared to 3, compared to 4. Instead of x, we're going to have time. Instead of y, we're going to have distance. Mike, I forgot to ask, can people talk to me?
So definitely, if you want questions asked during the presentation, we can have them raise their hands and we can call on them. Because right now I think we would have to unmute them, but we need to know in advance if they do have a question.
Okay, here's a question I'd like to ask all the students. I asked you to think about what's different from quadrant 1 compared to quadrants 2, 3, and 4. Can anybody tell me what's different about quadrant 1 compared to 2, 3, and 4?
Okay, it looks like,
Can you hear Mr. Aguilar?
yes.
The lady said everything's positive in quadrant 1.
Perfect. Everything's positive in quadrant 1. And since none of us older people have been smart enough to figure out negative time, hopefully one of you students can do that really soon. We can't use negative time. So we can't use quadrants 2 and 3. And we pretty much can only travel a distance in a positive direction. So we have to use quadrant 1. And that's the quadrant we use to draw time distance diagrams. So here we go. X-axis is time, y-axis is distance. We're in quadrant 1. Time we measure in seconds because green lights have a certain length in seconds, and the evil red lights have a time also in seconds. We measure distance in miles, but it's a little bit different than that. We really don't care about time. Sure, if we're driving somewhere and we're late, we worry about time. But what we really worry about if we're driving on a road is whether the light is green or red. So we use time measured in seconds, but that's just kind of an interim step. To get to what really matters is the light green or red. And we really don't use distance except as an interim calculation. What we worry about is upcoming intersections. So here we have a north-south street. We've got a street A, which is an east-west street, and a street B, which is an east-west street. And we're going to drive from street A to street B. Okay, I'm going to ask you a question. That little white line that just appeared on the screen, tell me a mathematical term for that white line, please.
I'm not getting anybody to respond to that.
Okay. Thank you, Rudy. I will tell you, and I want you to remember back to your high school and middle school mathematics teachers, because I am certain they use this word. The word is slope. The white line represents a slope. For our time distance diagrams, we don't use the word slope, but all of us smart, mathematically inclined people know we're using a slope. The slope, you've heard this expression, rise over run. The run is the x-axis, time. The rise is the y-axis, distance. So now tell me the word that traffic engineers use instead of slope to define that line. Go ahead, please.
They said speed.
And speed is exactly correct. Well done. Distance divided by time is speed. Okay, I drew this line in miles per hour at 36 miles per hour. Whoops, I got ahead of myself a little bit. Better said, I got behind myself a little bit. Okay, now we're going to drive from street A to street B. There we go. Because we're driving at a speed. We don't know it when we're driving, but we're driving along a slope that's a line that's in a Cartesian coordinate system. The line is drawn at 36 miles per hour because in this particular example, the signals are timed so that if you drive 36 miles per hour, you will get green lights at every single intersection. Pretty cool, eh? Obey the speed limit, all right? That gives you more green lights than if you speed. Let's look at this a little bit more. What happens if we drive too fast? The slope becomes more vertical and we arrive at street B in a red. If we drive too slow, the slope becomes horizontal and we arrive at a red light. Don't do that, okay? Obey the speed limit. And on a polite day, respectfully suggest to your parents or to your friends that they also drive the speed limit. It's safer and they see more green lights and fewer red lights. Okay, we don't time traffic signals for just one car, just one green light. There are lots of green lights and there are lots of cars for every green light. So we have these gray bands and this black arrow showing lots of cars on lots of green lights, driving from street A to street B. That's going northbound. We also have to worry about going southbound. So our time distance diagrams have to worry about both directions. I'm telling you people, Traffic signal coordination is hard work. We have to be highly skilled at mathematics. Notice that the northbound and southbound gray bands cross in the middle. So if we put a street C in the middle, all those cars will get green lights at A, at B, and at C. Street C happens to be 1/2 mile from street B and 1/2 mile from street A. And that's why we get consecutive green lights at all three intersections. Excuse me, Michael, I'm going to ignore the chat and just keep talking. And if you need to interrupt me, please do so.
Definitely, I'll keep an eye on it.
Excuse me, so here we go. Everything's fine because we've got this street C, 1/2 mile away from street A and street B. And the slope works great in our Cartesian coordinate system. So all is great. Now we're going to put in a street D at a bad location. It's a 1/4 mile from street A, a 1/4 mile from street C. Now we're going to draw some white lines that represent speed that are actually slopes in the Cartesian coordinate system. All's good with that car. Got a green light at all the streets. Second car, not so lucky. That car, driving 36 miles per hour, arrived on a red light. Same thing with the third car. Now we're going to add a fourth car. Fourth car got 2 red lights. When we got to street D, there were cars in the way. Even though that fourth car, this furthest to the right arrow, arrived on a green light, they couldn't drive through the intersection because there were 2 cars in front of it. And that's what happens with a badly timed signal system. Cars get in each other's way. And even though the light is green, we're forced to stop. Now let's look back. Let's get rid of that street D and look at these dashed yellow sloped lines. Everything is great for those cars because street D didn't exist. Without street D, we get green lights at streets A, C, and B. And we can even improve things a little bit so that more vehicles can receive consecutive green lights. So that's the first topic, traffic signal coordination, using the Cartesian coordinate system, the knowledge of slopes and speed being distance divided by time. Now let's move on to the second topic. This topic, again, this presentation that I'm giving you right here, I gave in the undergraduate junior level course I teach at ASU on transportation operations. So let's start with a typical signal, let's start with a typical intersection. We've got an east-west street, 2 through lanes in each direction. We've got an eastbound left turn lane, no signal, no stop signs for the east-west street. The north-south street, we've got a northbound through lane and a southbound through lane, and we've got a northbound left turn lane. So here we go. I'm going to push the little mouse left button and cars are going to appear. Cars going east and west, everything's wonderful. We've got a northbound blue car, wants to make a left turn, starts to, and a bad thing happened. That was kind of fast. Let's watch that again. Same intersection, everything's the same. Just going to show it to you again. Watch carefully, please. Driver of the blue car waiting patiently. and then decides to go. Now I'm going to ask you another question. Why did that collision happen? Okay, yeah, I drew it that way. Well, go ahead.
They said that the person wasn't looking, I guess, because we all saw the car there.
Exactly correct. That's one possibility. The driver of the blue car was not looking. Okay, please understand, the driver of the blue car is confined to planet Earth because he's not Elon Musk or Jeff Bezos or one of those other people that has his own spaceship. So he couldn't see the intersection from our vantage point. So yes, that is one possible reason. The driver of the blue car just didn't look. Is there another reason? Well, there is. Can you
Well,
guess?
the blue car was going to turn left and then the red car was just going forward. So the blue car would have had to pass to like go to the left because that other lane was for the red car. So just the positioning of the lanes made it a bit inconvenient for them to turn.
A good answer. That's part of it. Talk about that red car again. Tell me what that red car was doing.
Going forward.
Correct? The red car was going forward eastbound. The red car was moving. What does that tell you about the red car? The red car was moving. Was the red car moving fast or slow or Goldilocks? Just right. What do you think would have caused the accident? If the car was driving too slow, would that have caused the accident?
It might have been going too fast because it had already built up momentum since it had been driving previously.
Exactly right.
That's what they're saying here. Sorry, that's what they're saying here also. They think that, is that a red building that might be in the way they can't see, maybe? That big red box?
Exactly correct. Well done, everybody. Those are the three issues we have here. The driver of the blue car may not have been watching. The driver of the red car may have been driving too fast. And the problem is this red box that represents a building. So we're going to use high school and middle school mathematics, geometry, to analyze the circumstances of this collision. And let me tell you, I learned about this about 40 years ago, maybe 45 years ago, when I worked for a company that was involved in lawsuits against public agencies. And what our clients, the attorneys, did in the courtroom is prove. Well, the attorneys used our analysis, because we know high school geometry, to prove that this collisions just like this, was caused by a public agency not doing their job correctly. And I'm here to tell you, I made a lot of money suing public agencies because the public agencies didn't do a good job. And people were paralyzed or had serious brain injuries or had serious organ damage. Our friends, the people who taught us geometry, had the answer. Now I'm going to show you that geometric solution to this problem of an accident. So let's look at this intersection more carefully. As traffic engineers, we've calculated that for that left turn to happen requires 8.5 seconds. That gives the driver of the blue car time to look to their left, look to their right, accelerate at a proper, safe, comfortable rate, and get into the westbound lane so they can continue on their way. What happens during that 8.5 seconds that blue car is the driver of the blue car is looking left and right and then accelerating through the intersection? What else is happening?
The red car isn't noticing whoever is in the blue car because they're like looking both ways. So it's more time that the red car isn't halting because they can't see the blue car.
Almost. Let's not think about the
We think
driver
it's
of the
the
red
fact there's no
car.
light. There's no lights, it's just a stop sign. So the red car probably doesn't need to stop at all. Like there's no traffic signals, it's a stop sign.
Exactly
one
correct.
One
The red-
direction.
The red car doesn't have a traffic signal, doesn't have a stop sign. Let's not think about the driver and the driver's behavior. Let's think about that red car. What is the red car doing during that 8.5 seconds? You almost said it. Think about it a little bit more. Think back to that time distance diagram. Think about what that white line slope represented. What is the red car doing during that 8.5 seconds?
Trying to. What was that? They said trying to stop, and then some say they're trying to speed through. So I'm getting different responses.
Okay, yep, it's not obvious. It will be when I tell you. Think more simply. Just think about what the red car is doing. Okay, I will tell you. And you knew with your answers, but
We did have someone type in the chat moving forward.
exactly right, exactly right. The red car is moving. During that 8.5 seconds, if the red car was just sitting there stationary, there would have not been a collision. But the red car was moving. And one of the things that we do, one of the thought processes that we do as engineers, applied scientists, we get down to the very simplest facts. The blue car needed 8.5 seconds to make the left turn. The red car was moving during those 8.5 seconds. That's what caused the collision. Not putting any blame on anybody. That's just the facts of the collision. Blue car moving, red car moving. Let's understand that a bit more. The driver of the blue car is looking to his left. The building represented by the red box is obstructing the vision of the driver of the blue car. Notice where I drew that blue dashed line. I don't care if the driver of the blue car is looking or not. According to this blue line, if they look to the left, can they see the red car? What do you think?
No, they don't see it right now.
They don't see the red car. The driver of the blue car could well be looking for traffic, like we're all taught in driver's education classes. They're being careful. It's not their fault the crash happened. They were looking, they couldn't see the red car moving. They didn't know it was there. And that's why the crash happened. Let's keep analyzing this a bit. Let's look at the picture a little bit more focused. Let's put in some dimensions. What we're going to use is Pythagoras, what he taught us. We've got a green triangle here. The hypotenuse of the green triangle, the diagonal side, is the driver eye visibility from the blue car driver to the red car. And then the short side of the triangle is north-south, vertical, and the long side of that triangle is east-west, it's horizontal. So the direction of travel of the blue car, at least initially, is they drive straight, and then eventually they turn left. But right now, they're just driving straight, represented by the short side of the green triangle. The long side of the green triangle is the travel by the red car. We can understand, we can understand this distance, the short side of the green triangle. We really don't know this distance because the red car is moving, okay? Blue car stopped, so we can define that. Red car is moving, so it could be anywhere along this line. So the distance on the east-west street in this green sight triangle is unknown. But again, thanks to Mr. Pythagoras several centuries ago, we can devise a way to calculate the distance on the east-west street. And what we use is this yellow triangle. Okay, please tell me what your high school or middle school geometry teachers taught you about these triangles. There's a certain expression they use for this yellow triangle and this green triangle.
Yeah, that's they are similar triangles.
Exactly. Because of the laws of similar triangles, we can determine, oh, go ahead.
Sorry, I was talking to a kid.
Oh, no problem. We can use the laws of similar triangles to define the dimensions of the yellow triangle. And with that, we can then determine the dimensions of the green triangle. And I need to kind of talk a little faster here. I've only got 25 minutes left. So we need to put in some dimensions to tell us where the building is relative to the street. So it's 43 feet west of the north-south street, 13 feet south of the east-west street. We'll add in 12-foot lane. Traffic engineers use 5 feet from the center line to the driver eye. And then over here, you should be able to see a dimension of 16 feet from the edge of the east-west street to the driver eye of the blue vehicle. Knowing those dimensions, we can then define the dimensions of the yellow triangle. The north-south side of that is 3 feet. The east-west side of that triangle is 60 feet. Good. That tells us the yellow triangle dimensions. The green triangle, the north-south dimension, we know to be 23 feet. Knowing those dimensions, we can calculate this unknown on the east-west street. And this diagram is just a repeat. So you can see where I got those various dimensions so that I could calculate the dimensions of the yellow triangle and then use similar triangles to calculate the dimensions of the green triangle. So here we go. We're going to use similar triangles. The dimension we want to know on the east-west street is unknown. We've got the north-south distance of 23 feet for the green triangle. And we've got the dimensions for the yellow triangle of 60 and 3. So we can calculate, because someone taught us division and multiplication, we can determine that this unknown distance that the red car travels is 460 feet. Knowing the red car travels 460 feet, knowing that the blue car needs 8.5 seconds to make that turn safely, what can we determine? We know a distance in feet. We know a time in seconds. What can we calculate?
Slope.
We
Speed
calculate slope,
and the speed.
and therefore the slope that we use is the word speed. We can calculate the safe speed of that red car. So we do. And yeah, we've got an available sight distance of 460 feet. Now we can calculate. We don't use feet per second, we use miles per hour. So we have to do some conversion. Distance divided by time. Safe speed for that red car is 36.9 miles per hour. So if that red car is going 36.9 miles per hour or less, collision won't happen. So what us traffic engineers do is we have signs just for drivers to tell them what is safe and tell them what is approaching. Better said, tell the drivers what they are approaching. This little black cross, we call it an advanced intersection warning sign. Down here, we have a speed plate. So now what we're going to do is we're going to add something to the street system. We're going to add this sign so we can tell the driver of the red car they should drive 35 miles per hour so they don't have to ruin their day by crashing into a blue car. Now let's watch what happens. Thanks to those good traffic engineers. Blue car's waiting, waiting. Red car comes. Blue car makes the safe turn. Why was it safe this time? What prevented the collision?
The slower speed. I mean, the slower,
Exactly
slower
correct.
traffic speed.
Lower speed of the red car, because a smart traffic engineer, thanks to his high school geometry teacher and his grade school teachers who taught him the 4 functions, him or her, sorry for using only male pronouns. The intersection is now safe, and it's only safe because the driver of the red car obeyed this warning sign with the speed limit of 35 miles per hour. So that's the second topic I wanted to tell you about, intersection sight distance analysis. And again, think your mathematics teachers, okay? Now I want to show you something else. You've all heard of photographic enforcement. I'm willing to guess that most of your parents and most of your friends hate PhotoRadar, hate it, and wish it didn't exist, because to them, it just forces people to either drive the speed limit or get a ticket. Well, I'm going to show you the other side of that, forcing people to drive the speed limit. This is not gory, but I'm going to show you a vehicle collision. Let's watch. Not so good. Let's see that again. This is obviously a video of a real collision that occurred at an intersection in the city of Scottsdale a few years back. Let's learn a little bit more about this. Think about being a passenger in this white car right there. Think about the driver of this black car and know that the red light appeared 9.62 seconds before this image was taken. The black car saw should have, the driver of the black car should have seen the red light 9.62 seconds before the driver got there. Again, think about being this passenger. Think about what that passenger is feeling right that instant. Good news is it was only half a second before this collision occurred. So that terror only lasted half a second. The speed limit on this street, the north-south street, street of the black car, was 45 miles per hour. The driver of that black car was traveling at 70 miles per hour. I want more than disciplining the driver of that black car. That driver ignored a red light, ignored it by 9.62 seconds. And the driver of that black car disobeyed the speed limit of 45 miles per hour by traveling at 70 miles per hour. I want the driver of that black car persecuted. I want them punished. I want them to never, ever drive again because they inflicted damage on people in the white car who did nothing wrong. So please remember this little story. And if somebody you know starts complaining about PhotoRadar, tell them the story of this video you just saw and tell them that's why traffic engineers and police departments have photo enforcement, have red light cameras. We don't like these events. We don't want them to occur. Having PhotoRadar minimizes these events. Going back to being a traffic engineer, I'm extremely proud that back in the mid-1990s, I was one of 3 people directly responsible for PhotoRadar in Scottsdale. The other 2 people were police officers, a lieutenant and a sergeant. We went before the Scottsdale City Council, made our position, made our recommendation known to the City Council. The City Council voted 4-3 to install PhotoRadar on Scottsdale Street. And this is why. Thanks for your attention to that. So there we go. That's my story, mathematics and traffic engineering. I've got a few minutes where I can answer questions you may have.
So definitely at this time, if you do have any questions, please either type them in the chat. And if you want to ask a question directly to Paul Basha, you can click at the bottom of the screen and the raise hand option, and then Bree will call your name. So go ahead and type your questions or raise your hand now. Bree, do you see any questions coming in?
Unfortunately, I'm not a co-host, so I don't think I can see some of the items like when people raise their hands.
Oh, okay.
But I do have a first question that we can ask. So Paul, how did you decide to go into this specific type of work, especially traffic engineering?
an interesting story. First off, when I was in high school, I really, really liked mathematics. My older brother was a high school mathematics teacher. I really liked science. I wanted to apply science. So I decided on a degree in civil engineering. One of my professors back in the early 1970s at Michigan Technological University, a fantastic school, I would recommend it to anyone, happened to be a traffic engineering professor, a very kind, very smart man. So I just wanted to be like him.
And what type of coursework did you have to take in your undergraduate degree to start preparing for this?
Had to take calculus, and I do know that in many high schools, calculus is taught. So I had to take higher level mathematics, and then I had to take, and I was fortunate enough to take specialized courses in traffic engineering. And now here I sit 50 years later teaching 2 of those courses.
So I do see another question. Which ASU college do you teach at, or are you a guest speaker there?
I am a faculty associate. I'm a full-time traffic engineering consultant. I teach 1 summer course and 1 fall course in the evening. It's the College of Sustainability and the Built Environment.
Perfect. And I don't see any other questions in the chat, but see, I know there was a hand raised, participant.
I have just a quick question about like engineering in general. Like, how do you prepare to apply for an engineering major in university?
Excellent question. Thanks for asking. And incidentally, I certainly hope to see you high school students in the year 2025 in one of my courses. The way you prepare to be accepted into a civil engineering or traffic engineering program is study mathematics hard. Really devote a lot of attention and a lot of time and a lot of energy into your mathematics coursework. Thank your mathematics teacher and all your teachers for that matter. That's the biggest way to prepare, study. And I'll even tell you that when it comes time for you to apply to become an engineering student at some university somewhere, reference this presentation. I hope I answered your question.
Yeah, I was also wondering, do you have any like extracurricular suggestions in terms of what we can do outside of school, kind of to get more into math and engineering?
Okay, I tend to be a rather philosophical, existential humanist. So my answer is spend time with people. Bear with me just a moment, please. To be a good engineer, you have to be a good person. You become a good person by listening and watching. So whatever you can do to be actively engaged with other human beings, do that. Thank you. Sorry. I really like my work. I'm pretty passionate about it. And so sometimes I have a hard time controlling my emotions.
Well, thank you very much for your presentation. It was very informative and very, very interesting.
You're welcome. Thanks for being here. Thanks for listening. Thank you all for your questions. My email address and my telephone number are on the screen. Feel free to call me. If you want to talk to me further about university applications, please do so.
So, Mr. Basha, we did get one last chat, or actually a couple in the chat comments, just Mo Haji and Rudy Aguilar. They were both thanking you for your presentation and your time today. And I do as well.
And you're all very, very welcome. Thank you very much for the invitation, Mike and Rudy and Mo. Very happy to have been here.
So if I could ask one last thing from you, no one actually sent me anything about any students on here who were attending. I know there's some in Rudy's class, and I know participant is. So is there possibly, Mr. Basha, a question that you could ask, and maybe the first person to type it in would be the winner of our HDR's donated a $35 Starbucks gift card. So I would like to give that away. I would like to not have to use it myself. So can you
Mike,
think of a
I'll share it with you.
That's an option too. That's an option too.
Let me ask you this question. In the first of the three presentations, I mentioned the Cartesian coordinate system. Can you tell me which quadrant of the Cartesian coordinate system we use and why?
Okay, I'm looking in the chat, or Rudy, I know you have some students there. Okay, participant said quadrant 1 because it has all positive values.
Excellent.
All right, so it looks like you are the winner. So I'll actually need to email you the gift card. So if you don't mind sending me your email address, I will make sure to put my email again once more in the chat right now. It's michael.book@hdrinc.com. Okay, yep. And thank you again, Mr. Basha, for joining us and presenting to us. The session has been recorded and it will be available on the WTS Metro Phoenix chapter website. As soon as it is available, I will send meeting participants the link to access. The link will also be available on the Transportation U AZ, Facebook, and Instagram social media sites. Please forward the recorded virtual event link to other teachers, students, or other individuals who would be interested, and please encourage them to join our other events for this school year or view the other recorded sessions. In addition, go to those sites for information for upcoming program events. One last thing, Mr. Basha. Someone asked about if you were giving any more of these presentations. Do you have any plans, or just they need to enroll in your class?
Well, I'd prefer they enroll in the class. I actually give a large number of presentations. I'll be speaking actually next Monday afternoon. I was just invited to participate in a panel. Yes, in our profession, traffic engineering and any engineering, and frankly, most any profession, we have professional associations we belong to. I belong to WTS as well as the Institute of Transportation Engineers. And these associations, excuse me, have monthly meetings. And if you go to those websites, WTS is one, ITE is another, you can see a schedule of lunch programs and a large number of very expert presenters speak at those luncheons. And anybody is welcome to attend those luncheons. And students are either given a very large discount or are allowed for free. So just go to those websites and follow them. And if you'd like, send me an email. I'd be happy to give you the direct email of those professional organizations.
Perfect. Thank you again, Paul. And I hope and I hope everyone attending has a safe and relaxing holiday season. Once again, I'm Michael Book. If you have any program or event questions or suggestions, please send me an email at michael.book@hdrinc.com. And again, thank you, Paul, for presenting to our group again today. And I will see everyone in January for our next event. Have a good day.
You're welcome. Thank you, Mike. So long, everyone.
Thank you.